Hello everybody, in this lecture we will be solving 1997 IMO problem number 5. Here is a view of this problem. We need to find all pairs of integers, positive integers a, b, that satisfy the following equation: a raised to the power b squared is equal to b to the power a. I would like to have a case work where the first case is when we have a less than or equal to b. Obviously both a and b are already known to be greater than or equal to 1. Now I can rewrite the left hand side as a to the power b raised to the power b, which is equal to b to the a. And now because the exponent on the left hand side is greater than the exponent of the right hand side, it must be that the base of the left hand side is less than the base of the right hand side. So therefore the base of the left hand side is a to the power b must be less than or equal to b. Now recall that in this expression a is greater than or equal to 1. Now it is not too hard to show that in fact, here we note that this expression will have no solution for a strictly greater than 1. And to see that, you can just observe that this is an exponential form versus this side is a polynomial. And for instance, if we replace a with any positive integer greater than 1, we would realize that the left hand side would be strictly greater than the right hand side. For example, if we consider the case of the least of these, a is equal to 2, we would have 2 to the power b, and I claim that this is strictly greater than b for every b greater than or equal to 1. There are numerous ways to prove this. You can make a graphical representation, for instance. Let's quickly do that. So this function, 2 to the power b, will look like this. So when b is equal to 0, it will hit the 1. When b is equal to 1, it will hit 2, like here, and so on. And then it's exponentially increasing, versus the right hand side is just equal to 0 at 0, and then 1 at 1, and then that's it. It's a linear function. So therefore it is obvious that the left hand side would be strictly greater than the right hand side. An alternative way to prove this would be by induction. Assuming that this is true, and knowing that for b is equal to 1, we have 2 is greater than 1, we can simply check 2 to the power b plus 1, which is simply equal to 2 times 2 to the power b. But by the induction step, we already know that 2 to the power b is strictly greater than b, 2b, and finally 2b is which is equal to b plus b. Obviously, if you replace one of the b's by 1, would be greater than or equal to b plus 1, and we are done with our induction. Okay, so therefore there is no solution when a is strictly greater than 1, suggesting that we can focus on our attention on a is equal to 1. And if in the equation you plug in a is equal to 1 here and here, the left hand side would simply be equal to 1. The right hand side is b, so therefore b comes out. So if a is equal to 1, then it implies b is also equal to 1. So therefore this is our first pair of solutions, 1, 1. Now for the rest of the problem, or we can call it case 2, we will assume that a is strictly greater than b. So therefore case 2, so a is strictly greater than b, which is greater than or equal to 1. So this is the main assumption that we will consider. Now let's have a look at our main equation again. B to the power a. Now look at these as the exponents and then these as the bases of the exponents. So because the base of the left hand side is greater than the base of the right hand side, it must be the case that the exponent of the left hand side, b squared namely, is strictly less than the exponent of the right hand side. So therefore, if I further multiply both sides of this expression by b to the power minus 2b squared, the left hand side becomes, because they have a so this expression, by the way, that we are multiplying is the same as b to the power minus 2b squared. So therefore our expression, so this expression becomes a b to the power minus 2b squared, right? And then for the right hand side, we have, multiplying with this, we would have b to the power a minus 2b squared. But because of this inequality, we observe that this inside the parentheses is strictly greater than 1, suggesting that the whole left hand side is greater than 1. So therefore the right hand side should also be greater than 1, implying that the exponent cannot be negative. So therefore a minus 2b squared is strictly greater than 0, which implies a in fact is not only greater than b squared but also greater than 2b squared when b is strictly greater than 1. Because if b is exactly equal to 1, the right hand inequality will be exactly equal to 1, so that won't work. So therefore we have further refined the bounds and the relationship between a and b. Now let's do a little bit more. Consider the expression inside these brackets here. Let's express this a over b squared in its simplest term as a simplest fraction as k over n, where k and n are integers, positive integers. So let this be the simplest fraction that represents a over b squared. So this would imply that in fact k is equal to right, an times let me write that down like this, n times n, a times b to the power minus 2. Now remember here k and n are in its simplest form, so their greatest common divisor must be 1, right? And we have this expression. Now I will take the b squared power of both sides of this expression, so I have k to the power b squared is equal to the b squared power of each of these terms. So we would get n to the power b squared, and then yeah, so we have a to the power b squared, and the other term, well, let's do it step by step. A to the power b squared times b to the power minus 2b squared. But recall from our original equation that this is just b to the power a. So therefore this would be equal to n to the power b squared times b to the power a, but then we have also this term here, a minus. So now what is nice is that we already know this is greater than 0, so we have an integer here. So this is a positive integer, and obviously this is a positive integer. So what it tells you is that n to the power b squared is a multiple, is a factor, a divisor of the left hand side, but it means that n itself must divide k. But it's impossible because we assumed that k and r are in its simplest form. So therefore this would imply that n is in fact equal to 1. Now therefore if I go back to this equation, I can simplify it. So we have that n is 1, so I can just get rid of it. So we have a is equal to kb squared, right? So from here we'll get a is equal to kb squared, and here k is a positive integer. Therefore I claim that, let me write it as a simple claim here, no proof will be needed actually. I claim that k must be greater than or equal to 3, And the reason is simple, proof, let's say, a one-line proof. The reason is because if a is equal to kb square, and knowing that we are inside this case here, we have already showed that a is strictly greater than 2b squared. Because a is strictly greater than 2b squared, it must be the case that k here is greater than or equal to 3. Now, having showed that, now we can insert this expression kb square into this guy here, and let me quickly do it actually. So we would get that kb square b to the power minus 2 raised to the b squared power is equal to b raised to the power a, we replace it with kb squared minus 2b squared, right? So I guess everybody's clear on this. But then this implies, so if I replace these, I have k to the power b squared is, and you can think of it like this, is equal to b raised to the power k minus 2 b squared, which is simply b raised to the power k minus 2 b squared. But then the exponents are the same, implying that in fact k must be equal to b to the power k minus 2. But we know from earlier, yes, we know from earlier that b is greater than, but b is greater than or equal to 2. So that would eventually cause a problem, because this is again an exponential form versus this side, the left hand side, is just a polynomial of the first degree in terms of k, right, in the variable k. So therefore so what we have is the right hand side in the so b to the power k minus 2 is greater than or equal to 2 to the power k minus 2, and in fact we will have that this thing is strictly greater than k. For instance, you can show it by induction again, like we did above. So whenever I think whenever k is greater than or equal to 5, notice that this strict inequality will hold whenever k is equal to 5, and you can simply use induction, and I just leave it to you as an exercise. So therefore, in fact, we have found that k is, knowing from earlier that k must be greater than or equal to 3. So therefore, k is equal to 3 or 4. Now, for these two values of k, let's see what pairs of a and b we can find. If I plug this into this expression here, we would first get that 3 equals b to the power 3 minus 2, which is equal to simply b. So b comes out as 3, and then going back into this expression, it would imply that a, which is equal to 3 times b squared, but b itself is 3 squared would give us 3 cubed, which is 27. So therefore 27 3 works. 27 3 is a solution. And finally, when k is equal to 4, so this one is when k is equal to 3, when k is equal to 4, we have that 4 is equal to b to the power b to the power 4 minus 2, which is equal to b squared, but b is a positive number, so implying that b is in fact equal to 2. And now again, plugging into this expression, we have a equals kb squared, a equals, but k is 4, k b squared, which is 16. So therefore another solution would be 16 and 2. So therefore the complete solution would be the 3 pairs that we have found, namely 1 1 from the first case, and from the second case we have 16 2 and 17 3, and we are done. Hope to see you guys in our next lecture.